The next section we'll be looking at is 4.4, looking at optimization. We've already done a bit of optimization before. So the first example is really a review problem. Find the absolute extrema. So we've talked about local or relative extrema, as in turning points. Here, this is just what you would think. This is the absolute highest or lowest point on the graph of f of x. So in other words, because I'm looking for the absolute highest or lowest point, a function would have only one absolute max and absolute min, whereas it could have multiple local maxes or mins. So here's number one. Let's look at f of x equals, let's do x cubed minus 2x squared minus 4x plus 4. So this is a polynomial function. So very similar to many examples we've done before. So I'll start by differentiating. So let's see, 3x squared minus 4x minus 4. And then I'm going to say, okay, so if I'm looking for extrema, maxes or mins, I'm looking for where is that first derivative equal to 0. In other words, where is the slope of the tangent line 0? So then I have to factor this. Let's see, I need a 3x and an x. Let's see here, multiplies to 4, maybe, would it be minus 2 and plus 2? Let's see if that works. So that would be 3x squared, that'd be minus 6x plus 2x is minus 4x minus 4, looks correct. So my critical numbers for this polynomial are negative 2/3 and 2. So now I have a couple options. Let me find the second derivative, and then I'll use the second derivative test. So my second derivative, let's see, it's going to be what, 6x minus 4? So now I'm looking again at the second derivative test. So remember how that works. I take one of my critical numbers, like say negative 2/3, and then I evaluate the second derivative at that critical number. So I'm plugging that negative 2/3 into the second derivative here. It's going to be 6 times negative 2/3 minus 4. This is going to be less than 0. So let's see then, if the graph then is concave down at x equals negative 2/3, then again I know that I have a local max at x equals negative 2/3. And then I still have to find the corresponding y value. So for that, I have to actually plug the negative 2/3 in the function. So here was the function. So let's see, I'm going to have negative 2/3 cubed minus 2 times 2/3, or negative 2/3 squared, minus 4 times negative 2/3 plus 4. Okay, so now I have to get this simplified. So I'm going to need a common denominator. So I guess that would be 27. So I have negative 8 over 27. So I'd multiply this by 3 over 3. So that's negative 24 over 27. And then multiply this guy by 9. What is that, 72 over 27? And then, let's see, 27. Is that 108? Okay, so that's negative 32. Well, let's do it this way. So 108 add 72. That's 180. Takes care of these two. And then let's see here, I have 24, 32, so minus 32. So what is that? 8, 4, 148. So now we know the coordinates of the local max then. So that would be at our negative 2/3 and then 148 over 27. So now let me look at, where was the other critical number? Back here, 2. So now I'm going to look at x equals 2. And I'm going to say, what is the second derivative evaluated at 2? So our second derivative was 6x minus 4. So let's see, if I plug 2 in there, I get a positive number. So then the graph is concave up or at x equals 2. So in other words, I'd have a local or relative min at 2, comma, now let me find f of 2. So here was that function. So let's see, if I put 2 in there, let's see, 2 cubed, that's 8, minus 2 times 4 minus 4 times 2 plus 4. So that's 0, so what is that, negative 8 plus 4? Negative 4. So my local min would be at 2, negative 4. So let's see, I have my local max here and my local min here. Now the only thing I'm thinking about is, remember that I was supposed to be finding the absolute extrema. So I have the local max and min. The only thing I'm wondering is what happens on the ends of this graph. So let me look back at the function for a second. So let's see here, I have a cubic function. So if you remember what a cubic function looks like, on the left side, the graph's going to go down. On the right side, the graph's going to go up. So I'm just thinking really roughly, about what this graph might look like. So I have this local max at negative 2/3, and then what is that number? 148 over 27. So I don't know, I'm going up, and then I hit this local max. So there's that point. And then my local min is over at 2, negative 4. So there's 2, negative 4, and here's that kind of ugly point, negative 2/3, 148 over 27. So in this case, because the ends are just going to positive and negative infinity, those wouldn't count as extrema, since those are not really points. So we can see the local max at negative 2/3, 148 over 27, and the local min at 2, negative 4. But again, since the ends of this graph tend to positive and negative infinity, actually in this case, we're looking for absolute extrema. In other words, the absolute highest or lowest point on the graph. Actually, since this guy continues to negative infinity and this one to positive infinity, actually in this case, if we're looking over the whole domain, we would say this function has no absolute extrema. But we could restrict the domain. We could say something like find the absolute extrema, say on, I don't know, the interval negative 2/3 to 2. So in that case, then we would only be looking at this interesting part of the graph, say from here to here. And in that case, then we would say we have an absolute max at that negative 2/3, 148 over 27, and an absolute min here at 2, negative 4. But that would only be if I'm looking just at this segment. So what about for a number 2? Let me look at something like f of x is x to the 2/3. But let me look at this guy specifically on the interval, or in other words, for x's in between negative 1 and 8. And again, I'm trying to find, the example's the same, find any absolute extrema. So I'd start the same way. I'd still find the first derivative. So that first derivative, let's see, that would be 2/3 x to the negative 1/3. Let me see, so that's the same as what? 2 over 3 times the cube root of x. All right, so then I'd have to look for two things. I'd have to look for where is this equal to 0? Well, actually, this guy is never equal to 0, because if I set this to 0, I'd get a false statement, 2 is equal to 0. So then I have to say, what about where f prime of x is undefined? So actually, this guy has a critical number at x equals 0, because x equals 0 is an x value for which the derivative is undefined, but actually 0 is in the domain of the original function, because if I was to plug 0 in here, I would just get 0 out. So that's my critical number. So now I have a couple options. I could use the first or second derivative test. I don't know. Let me try the first derivative test. So let's see if we remember how this works. So for this, I'd set up my sign chart. Remember, this sign chart is actually for the first derivative. That's right here. So if I plug any positive number in the first derivative, well, I'm going to get a positive number out. Cube root of a positive is positive. Versus if I plug any negative number in here, well, the cube root of a negative is negative. This expression is going to be negative. So I can tell you this function is decreasing on negative infinity to 0. It's negative, first derivative, and increasing on 0 to infinity. So if that's the case, let's see, I mean, if it's decreasing, 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 increasing, 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 well, then I know at 0, I must have a local min. At 0, comma, well, this one's at least easy. If I plug 0 in the original function, well, I just get 0. So I know I have a local min at 0, 0. The only other thing I'm wondering about is, remember, they said I'm only interested in this function for x is in between -1 and 8. So I really only have a segment of a graph here. So I'm just curious what happens on the ends. So let me look at the ends. Next question, what happens on the ends? In other words, so let me look at that first value, x equals -1. And let me say, what happens if I actually plug -1 in the function? So that would be -1 to the 2/3. So I could say that's the cube root of -1 squared. Well, that's just the cube root of 1. It's 1. What about the other end? The other end was 8. So what about f of 8? So f of 8, I would have to plug 8 in here. So that would be 8 to the 2/3. In other words, that would be the same as the cube root of 8 squared. So that's 2 squared, so 4. So what the heck does all this mean? If I was to just do a rough sketch, just kind of based on the information that I found, an idea what's going on. So I know I had a local min at 0, 0. Put that here. On the end, so at x equals -1, the y-coordinate was 1. So I have a point, you know, right here, -1, 1. And then at 8, the y-coordinate was 4. Just a rough sketch. There's 1, 4. And what else did I find? So decreasing -infinity to 0. But I guess in this case, I mean, we're only interested in the interval -1 to 8. So really, I mean, I'd just say I'm decreasing from -1. Let's see, where were we? To 0, right? So decreasing, 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 decreasing. And then let's see. Increasing on 0 to infinity, or I guess we're really just looking between -1 and 8. So I guess I would say increasing, you know, from 0 to 8. Now I'm being really rough with my sketch here because I didn't actually find the concavity. Not really necessary. But I could conclude based on this. Let's see here. You see how I can see this local min is actually the absolute min. So this function has an absolute min then at 0, 0. That's this guy. And actually this endpoint here would be the absolute max. So the absolute max was actually that point at, what was that, 8, 4. So there's all my information about this function. how about one more like that? So for number 3, let's look at, this guy's called g of t equals t over t minus 1. So I have a rational function. Okay, so what if I ask specifically, let's look at this one on the interval, let's see, how about 2, 4. So I'm looking for, again, find the absolute extrema. Same thing. So let me start the same way. I'd have to start by finding the derivative. So quotient rule, let's see, so the bottom squared, derivative of the top is 1 times the bottom minus derivative of the bottom times the top. So that's going to be what, t minus 1 minus t? So let's see, negative 1 over t minus 1 squared, my first derivative. So this one's kind of interesting. So here's my first derivative. So then I do my analysis. So in order to find an extrema, I'd have to say, okay, well, what is going to happen with this guy? Is this first derivative ever equal to 0? Well, no, because if I clear the fraction, I get a false statement. Negative 1 does not equal 0. Okay, so then there are no local maxes or mins. So then the only other thing I'm looking at is, well, where's this guy undefined? Well, it's undefined at 1, but remember 1 is a vertical asymptote of the function. So if I set up like a first derivative test or a sign chart for the first derivative, what I'm really looking at here is I actually don't have any critical numbers. I don't have any potential local maxes or mins. Look, so here's 1, but remember 1 is the vertical asymptote. So this time I'm looking at values of t. But the thing is, if you look at this first derivative, any value that I plug in here, the denominator squared. So I'm going to have a negative over a positive. So actually, isn't this function then always decreasing, or at least across its domain? So decreasing on negative infinity to 1, and then again from 1 to infinity. So, well, I mean, look, if I do a rough sketch, I guess this is t and this is y. So here's my vertical asymptote, t equals 1. Now remember, let's see, we talked about finding the horizontal asymptote. I look at the degrees, the leading terms. See how I have t over t? Actually, the t's would just cancel out and t over t would leave me 1. So my horizontal asymptote would actually also be 1, but y equals 1. Well, any other information I could find? Well, I could find the intercepts very easily. If I set t to 0, I get 0 over negative 1. So that's just 0, 0, right? Now, actually, if I set the function to 0, the y to 0, I still get t equals 0. It's just the origin. And then what else do I know? Well, I know this function is decreasing across its whole domain. So it has to be decreasing, 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 and then decreasing, 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 decreasing. So I can pretty much see already what's going on. The only other thing I have to look at is, well, I was looking specifically on the interval 2 to 4. So actually I'm not looking at this complete graph. Because if I was to draw in this complete graph, I mean, look something like this, right? So remember, I'm looking specifically on 2 to 4. So what about the ends then? In other words, what happens if I plug in t equals 2, say, to the original function? So I'm going to plug in 2. So I'm going to have what? 2 over 2 minus 1? 2 over 1? So g of 2 is 2. So let me look at the graph. So here's, 2 and 2. So there's that point. Seems to match. Okay, what was the other one? 4. So now I need to know what is g of 4. So let's see, that'd be 4 over 4 minus 1, 4/3. So where's that? 4/3 is a little more than 1. So 1, 2, 3, 4. 4/3 is right here. Try to label that 4 4/3. But actually you can see here, so this is the region that I'm interested in. Just this region here. So I can tell you then, based on my analysis, I can see my absolute max and my absolute min. So let me just write them out then. I'd have an absolute max at 2, 2, right? Because I'm only interested in this segment. So on that segment, that's the highest point. Versus this guy is my absolute min. And that one is 4 4/3. And so there's my information. So I thought we would look at one little application problem. So let's see what we have for this example. It says the height of a rocket and that is in feet, t seconds into flight, is, let's see, this is given by f of t equals, let's see, negative t cubed plus 96t squared plus 5. And then let me see if I can answer a couple of questions. Say find the max height. Okay, so let me find the derivative. So that would be negative 3 t squared plus, let's see, what is 2 times 96? Is that 192? T. Okay, then let me set this to 0. And then factor out negative 3t, the GCF. That would be t. And then what is 192 divided by 3? 6, 18, 64. So then looks like my t values would be 0 and then 64. Okay, so then let me do some analysis here. So let me make a chart for the derivative. I'm interested in 0, 64. So let's see, if I look at my derivative, well, let me pick a number in this interval. Like say maybe 1. So that's going to be -3 plus 192. So positive. This is positive. Well, so let me see. If I take a big number, let me look at something like 100. See if I can figure out the sign. So let's see, if I plug something like 100 in here, well, this is going to be what? -300. So I'm going to have a negative here. And then let's see, 100 minus 64, positive. So this is a negative number. Okay, so what's happening then with my rocket? So that rocket's height is increasing on 0 to 64. Then decreasing. Now, I guess I wouldn't say to infinity. I guess I would say it's decreasing, you know, until it hits the ground. Didn't actually determine when it would hit the ground. So let's see. If it's increasing till it gets to 64, then it starts decreasing. Well, I guess the max height then would have to occur. It's increasing, decreasing, would have to occur at 64, t equals 64. So the max height would occur at t equals 64. Now, since the question actually asked for the max height, I guess I would have to determine what is f of 64. So that's looking at this guy. So that'd be what? -64 cubed. And then what's the rest of this? Plus 96 times 64 squared. And then plus 5. So for this part, the numbers are a little big. I think I used a calculator for this guy. I got 131,077 feet. So this would actually be the max height. So what about one more part to this one? For the same rocket, let's ask what is the max velocity? So if I'm looking at the velocity, I'm looking at the first derivative. But if I'm looking for the max of the first derivative, well, in order to find that, I'd actually need the second derivative, because I'd actually need to set that to 0 in order to find the max of this first derivative. So my second derivative would be what? Let's see, it'd be -6t plus 192. Okay, so if I set this to 0, get negative 6t plus 192 equals 0. 6t equals 192. So t equals, what is that, 192 divided by 6? 32. Okay, so at t equals 32, at 32 seconds, the max velocity is reached. So what is the max velocity? Well, that I would have to plug 32 into the first derivative. Remember, the derivative represents the velocity. So if I plug 32 in my first derivative, so that would be negative 3 times 32 squared, and then plus 192 times 32. Can I get this one without a calculator? Let's see, if I factor out my GCF, my 32, see I'd have a negative 3 times a 32 plus a 192. So that would be, let's see, what is that? Negative 96 plus 192. So that's what, 96 times 32? Well, so this might be calculator appropriate. Looks like 3072 feet per second is my maximum velocity.